So we're going to look at a concept that is reminiscent of single variable calculus, the concept of critical points, and see how this will translate into multiple variables. So if we have a given x value and it's called a critical number of a function, then that means when you substitute the number into the function, it's defined, or that means it exists, or you could say there is a point on the graph there. Those are possible ways of viewing that statement's defined. And we learned that the point where there's a critical number has to have another condition with derivative, and so one of those conditions was the derivative is 0. And that could happen at a place that was at a local or relative minimum, or a local or relative maximum, or in the case of x to the third power, I kind of tell my students it's like the graph gets tired of going uphill, has to catch its breath, okay, and then it goes up again. It's a critical point because the derivative is momentarily 0, but the function increases forever from left to right. Well, the other type of situation where there's a critical number is if there's a point on the graph but somehow the derivative is undefined. So if it's a function, the cube root is a pretty good example of that. There's a point at the origin, but if you were to find the derivative there, you would find that there's a tangent line that's vertical. So it does have a tangent line, but the slope of a vertical line is undefined, so there's no derivative there. Another case, it's not a function, but might be on a circle, on the right or left side of a circle. Again, there's a place where there's a tangent line, but the slope is undefined, so those would be called critical numbers of the function. Well, it's not a function, but it would be an important place at least, maybe not critical. And then there's another type of problem like y equals the absolute value of x, or y equals x to the 2/3 power, where we had a place where you simply could not measure the slope and there is no single tangent line there. There we go. Both of them have critical numbers at this sharp turn. So that was a critical number, and then we called it a critical point when you filled in the y-coordinate. So you'd say this was the point 0, 0. So that would be a critical point on the graph. The critical number was the input only. The critical point was the full location of the point on the graph. Now, let's take that Calc 1 and let's look at something that we have going right now. So let's consider one of our functions. F of xy equals 4 minus x squared minus y squared. So that would be, what kind of graph is that? Well, if your mental image is anywhere close to this, that would be great. Now, if I were to guess, I think that this point here, which looks like a maximum, might also fit that category of something that's called critical. But I need a definition to go with. So that's a question mark because I don't know, is it called critical? So let's look at a definition of what makes something critical in a multiple variable case. All right. Okay, let's see what we've got here. All right, it doesn't say critical number. It says this is a critical point of the function if, oh, there it is, exists again, or I should say that's the same as writing defined, right? That same possible terminology there. And something has to be true besides that. Okay. Let's see if I can just slide it a little bit more. All right, so this says that both the x and the y partial derivatives have to be 0 at the same time. That is a big ol' and statement. So we need both the x partial derivative and y partial derivative to be equal to 0 simultaneously. So the derivative is 0. So that would be this case we will find out later. Or if at least one of the partial derivatives is undefined. Now in the next set of video segments I may or may not get to studying this particular scenario too much. It helps to have some visuals of graphs to look at, but we're definitely going to focus on this one right now. We'll see what happens in the future. So let's see what this scenario looks like on a graph. Okay, so ready? What does it look like if both the x and y partial derivatives are 0 on a graph? Well, it could be a local maximum. So just like the paraboloid I hid from you from sight, now I want to be fair. On this particular graph, if it continues forever, it's an absolute maximum. Nothing is ever higher than it. But the definition of local maximum allows for the possibility that maybe the graph takes a turn and goes uphill afterwards, and it would be like some sort of a weird cake pan where there's a high point here but then it goes higher somewhere else. It's a local maximum. It's a local maximum. Of course, then that means we could have a local minimum. I'm using the paraboloid because it's the easiest to sketch in a hurry. And so that would be a place where both the x and y partial derivatives are both 0 simultaneously, here and here. There is a third category of point, and this one is kind of like the Calc 3 version of y equals x cubed. It's called a saddle point. And you would have met the saddle point earlier in the course. I might have even mentioned it in my own instruction videos. But the saddle point it's not a high point and it's not a low point, or you could argue it's both. So let me show you what I mean by that. For this particular graph, this point here would be called the saddle point. And if you've ever gone hiking in the mountains, if there are two mountains, you would typically, if you're trying to get to the other side, you would be hiking uphill. So you could argue that this is like a high point for you because that's the highest it's going to be. But it's also the low point between the two mountains. So it's really kind of both, or you could say it's not either. Again, we won't get philosophical right now. We're just going to just measure. That's kind of an unusual thing. This is another place where both the x and y partial derivatives are 0 simultaneously. Now, there are tools to help us identify which one is which. And here is where I'm going to sort of do a quickly show you case. Maybe someday I'll be able to provide a little bit more instruction on this topic. But for this next set, the next few videos, we're just going to pretty much put them to use. So let's talk about how to determine if you have a maximum, minimum, or a saddle. How do we know which one it is? All right, so first things first, there we go. A high or low point called extreme value can only occur either at the end or at a critical point. So this was a big similarity to Calc 1. If you had a closed interval, the highest or lowest points are either at the ends or at a critical point. That's just what this is saying. Now, so long as you can find derivatives, don't try to write this while I'm talking. Just listen, pause, come back and write. If you're using a textbook, you already have access to this in writing somewhere. Just listen to me sort of highlight it real quick. So let's suppose that we have the ability to take first and second derivatives, and they're continuous means there's no gaps in those derivatives. And we're looking around a particular set of coordinates, so there's nothing weird going on near the point on the graph. And specifically, we're going to look at the case where both derivatives are 0 at the same time. Okay, this is key. We're not looking at the undefined case in what you're about to see. If you want to find out if you have a maximum, minimum, or saddle point, here's what you do. Let me show you the first two of these. Now I paraphrased in writing here to not show the A and B in the notation because it gets really hard to see from the eyes. These are second derivatives. So this is a test, right? Test to see what kind of thing you have going here. So we got a maximum. If the x second derivative times the y second derivative minus the mixed second derivative squared is positive, which is basically just saying that the concavity, because second derivative measures concavity, I'm paraphrasing, this isn't quite mathematically pure here, that if you take the x and y second derivatives, that product is larger than the mixed derivative. This will be the same for max and min, but then if you have a second derivative that's negative, it must be concave down, which means you're at a maximum. And if the second derivative is positive, it must be concave up, so you're at a low point, a local minimum. If this term is bigger than that and you end up subtracting, get a negative number, then you have a saddle point. That's the graph I just showed a moment ago. Okay, you have one of those points right there. If you have a quantity equal to 0, then you have something that's inconclusive, a graph that's a little bit more interesting than those three. But we're going to start with looking at these three, and maybe someday again I'll be able to provide some more instruction here in terms of the public setting of this video. All right, kind of a lot to take in. My students will have access to this list of formulas. If you have a book, you have access already. My hand is probably not helping there, I'm guessing. Next time you watch one of these videos, we'll look at some actual problems. So, come on back.